Welcome to a video in which I introduce and describe floating point numbers. This video is part of a playlist on the RISC-V architecture and assembly language, but this video is completely independent of RISC-V. What I say here applies equally to RISC-V, ARM, Intel processors, and others as well. If you are familiar with floating point and the IEEE 754 specification, you can skip this video altogether and go straight on to the next video, which covers the specific RISC-V floating point architecture. But if you are new to floating point, then this video contains important material regardless of whether you're interested in RISC-V or not. In this video, I'll be describing how single and double precision numbers work. In RISC-V terms, you'll need to know this information in order to understand the optional F and D extensions, which cover single and double precision respectively. I'll be describing how floating point numbers are represented in binary, and I'll cover special cases like infinity, not a number, denormalized numbers, and other things like rounding and error conditions. As I said, this video covers the IEEE 754 standard. The standard is adhered to throughout the industry, including by ARM and Intel. The two most important parts of the standard cover single precision and double precision numbers. There are other sizes as well, but those are less commonly implemented. A single precision number is stored in 32 bits, or a word, while a double precision value is stored using 64 bits, also known as a double word. When you use the C programming language and you create a float variable, that would be single precision, and a double variable would be a double precision floating point number. In the RISC-V world, F applies to single precision and D applies to double precision, and sometimes you see those letters being used in describing the processor core specification. And for RISC-V, the single precision instructions all begin with an F, as shown here, while the instructions that operate on double precision values begin with a D. And if the processor implements double, then it will implement single precision as well. Let's begin with a review of scientific notation using this example, which is in decimal. We've got a sign, and then we've got the value, which is called the mantissa, and that is multiplied by 10 raised to some power. With binary, we've got the same idea. We've got a sign, and then we've got the value, which is made of zeros and ones, and that is multiplied by 2 raised to some power. So with decimal numbers, our exponent applies to a base of 10, whereas with binary floating point numbers, our exponent will be applied to a base of 2. With scientific notation, our habit is to put the decimal point just after the first digit, as shown here. And with binary numbers, we'll put our, well, we don't call it a decimal point, we call it a binary point or a radix point, just after the first 1 bit. This slide shows how we represent a normal single precision floating point value using 32 bits. We've got 1 bit reserved for the sign bit, and then we've got 23 bits to the right of the binary point here. So this green field is 23 bits in size, and then we reserve 8 bits to store the exponent. So that field is here. The initial bit is always a 1, so that's implicit and not actually represented. The representation of double precision floating point numbers is the same idea, only the fields are bigger. With double precision, we've got a 52-bit field for the mantissa, and we now have 11 bits for the exponent. So that gives us both a greater precision and a larger range for double precision floating point numbers. The term precision has different meanings depending on whether we're talking about scientific notation or floating point values. We might say that precision is imprecise. With scientific notation, the number of digits tells you about the accuracy of the measurement. So the number of digits itself conveys information. It tells you how close this value is to some ideal or correct number. With floating point values, the mantissa always has a fixed size, and so these additional zeros give you absolutely no information. Floating point numbers are just that. They are numbers with no additional information about how close or accurate they are. Every floating point value represents some particular rational number. But obviously, with a fixed number of bits, we can only represent a few rational numbers. So there are gaps between the values that we can actually represent. In order to give you a feel for this, I wanted to work through a couple of examples. And I'm going to start with this number, which is a very large number. And we have our 23 bits of precision for a single precision floating point number. And so what value is this number? Well, if we move our point, our binary point, over 35 places, we get this integer here. And as you know, every bit corresponds to some power of 2. So we have 1, 2, 4, 8, and so on, all the way up to these bits up here. And if we look at those in particular, we see that the number that we're representing is actually a bit over 79 billion. Which is a larger number that can be represented with an unsigned 32-bit number or a signed 32-bit number. So we have a greater range right off the get-go. And now let's ask ourselves, what's the gap between numbers in this range? So if we look at the next representable value, that is, we take this bit and we increment it to a 1, then we get this value here. And if we multiply it out, we see that this bit is in the bit position that corresponds to 2 to the 12th, or 4K, and it represents this value here. So we see there's quite a gap between these two values. The gap is exactly 4096, or 4K. But we see that these two values have the same first 7 digits when represented in decimal. So it's often said that with single precision floating point numbers, we have about 7 decimal places of precision. Okay, so that's a useful thing to keep in mind. About 7 decimal places of precision with single precision floating point numbers. We see that for very large numbers, the gap between successive values is very large. And with very small numbers, the gap between successive values is very small. So now let's take a look at a very small floating point number. Again, it's single precision, and we have a negative exponent. And if we shift our binary point to the left 16 places, we have this value right here. So as you know, with binary numbers, the place values are 1, 2, 4, 8, and so on. And that same pattern holds to the right of the binary point. So the place values are 2 to the minus 1, 2 to the minus 2, and so on. Or if we want to express that as fractions, 1/2, 1/4, 1/8, and so on. And so if we look at the value that we have here as in our example, these particular bits are in the places that have these particular values. So if we multiply that out, we get this particular representation in decimal. Now, as an interesting bit of trivia, notice that the binary representation has the same number of bits as the decimal representation has digits. That's always true. That's a bit of useless trivia. Okay, so now let's consider the gap between the values with these small numbers. So let's take this bit and let's go to the next number or the next value by changing it to a 1. And so here's the number that we're representing. And this 1 is way out in a position that has a very small multiplier, 2 to the minus 39. And if we multiply it out, you would actually get this value here. So here's one value, and here's the very next value that we can represent. And if you compare these values, you could see that the gap between them is, 2 to the minus 39th, which is this value here. And also, notice that the first 7 digits in the decimal representation is the same. So again, we say that with floating point numbers, we have about 7 decimal places of precision. And with double precision floating point numbers, we have about 16 decimal places of precision. So 16 decimal digits of precision with double precision floating point, and 7 places of precision with single precision floating point. With the floating point standard, there are actually several different kinds of things that we can represent. So far, we've just seen the representation of normal numbers, but we can also represent 0, infinity, not a number, and subnormal numbers, and these are distinguished by special values in the exponent field. With 0, the standard gives us both a positive 0 and a negative 0, and we also have positive and negative infinity, and we have something called not a number, and we have subnormal numbers, or also denormalized numbers. And these are numbers that are very, very close to 0. They have a reduced precision, and the positive and negative zeros are actually special cases of denormalized numbers. Now let me talk about exponents. With a single precision floating point number, the exponent field is an 8-bit field. And with this 8 bits, we can represent any exponent between minus 126 and plus 127. Actually, the encoding of these values is not the standard binary encoding, but you can ignore that trivia and just remember that the exponent ranges between minus 126 and 127. If the field is 80 bits, then that's used for these denormalized numbers, including our zeros. And a field with all ones is used to encode infinities and the not a number values. With double precision, it's the same kind of thing, except our exponent field is 11 bits, and we have a much larger range for our exponents. But other than that, it's the same idea. Here is how the infinities are represented with single precision floating point. If the exponent is all ones and the mantissa is all zeros, then it is interpreted as infinity. And we have a sign bit, so we can have positive infinity or negative infinity. And here are the representations in hex. And for double precision, it's the same idea. Now I want to describe subnormal numbers. Subnormal numbers are also called denormalized numbers, and they're used to represent values that are very close to 0. So here is the smallest normal number. We've got our implicit 1, but the mantissa is all zeros, and we've got the smallest possible exponent, minus 126. With a subnormal number, that implicit leading 1 is no longer there, and implicitly we have a 0 instead. And subnormal numbers are represented with an exponent field that's all zeros. And when our exponent field is all zeros, it's interpreted as the very same exponent, namely minus 126. So we can say the exponent is sticky, and it sticks at the smallest possible value. And with this particular subnormal number, we've got a mantissa of all ones. So you can see it's just slightly smaller than the smallest normal number. And if we keep going down closer to 0, we have a mantissa of all zeros except for a 1 in the least significant bit position. And that number corresponds to about 10 to the minus 45. And if we change that bit to a 0 and our mantissa is all zeros, then we have a 0 value. With the floating point standard, we also have the ability to represent something that is not a number. This would be, for example, our result if we tried to add positive and negative infinity. There's no particular value that would be appropriate, so we have the not a number value as our result. Actually, there are very many different bit patterns that correspond or are interpreted as the not a number value. All we require is that the exponent be all ones and the mantissa have at least a single 1 bit in it. It can't all be zeros, or otherwise it would be interpreted as infinity. So we have many values that correspond to not a numbers, and we ignore the sign bit. This particular value of all 1 bits is the canonical representation of not a number for single precision numbers. And if we happen to interpret this bit pattern as a signed integer, it would be interpreted as -1. With double precision floating points, we have the same basic idea. A not a number value is anything where the exponent is all ones and the mantissa is not all zeros. And here's an example of 64 bits representing not a number. But in this particular example, I'm not specifying what the lower order 32 bits actually contain. And with the RISC-V processor, in fact, we're going to use those low order 32 bits, and what we're going to do is we're going to hide a single precision floating point value inside. That's called the payload, and we'll have a single precision floating point value there. So we can interpret this 64 bits as a double precision not a number value, or we can look only at the low order 32 bits and we can interpret it as a single precision floating point number. Given that with floating point numbers we can only represent a finite subset of the infinite set of rational numbers, it's going to be the case that sometimes our operation will yield a result that is not exactly representable with a floating point value. So we're going to have to perform some sort of rounding operation. The IEEE standard describes several rounding operations. We can round a result down, or we can round it up, or we can round it towards zero. That is, we round positive numbers down and negative numbers up. But perhaps the most useful is to round the result to the nearest number that is representable as a floating point value. So we can always have a tie. That is, the exact result might be halfway between two values that are representable. So the spec requires us to round it to the nearest value that ends with a 0 bit. Okay, so that sort of prevents any kind of bias by sometimes rounding up and sometimes rounding down. So which rounding mode will be used? Well, that would be determined by the current rounding mode, and that would be set by some field in some sort of a control and status register. And with RISC-V, we have a control and status register that contains the current rounding mode to be used. Another thing to ask is what exactly can go wrong? What are our error conditions? And the spec describes these particular exceptional conditions that might arise after any particular floating point instruction. We've already talked about the result being inexact. So some operations will yield the exactly correct answer, whereas others will yield a result that was rounded. We can also have overflow, in which case the result would be either positive or negative infinity. We can also have underflow, where the result is a subnormal value, or possibly 0 itself. We can also have invalid operations. For example, if we try to divide 0 by 0 or add plus or minus infinity. And finally, we have the well-known divide by 0 problem. It turns out that this is not necessarily invalid. For example, 1 divided by positive 0 yields positive infinity, while 1 divided by negative 0 yields negative infinity. The spec describes that all of these exceptional conditions shall correspond to bits in some kind of a control and status register. So when the exception or error condition arises, the corresponding bit would be set, and those bits would be sticky. That is, they would stay set until they were explicitly cleared. So after a series of floating point operations, we could check the bits to see whether anything went wrong during the computation. At this point, I want to make a few general comments and warn you about using floating point numbers. So be careful. Floating point numbers, as represented in computers, are similar to, but are definitely not the same as, numbers, as mathematical numbers. Of course, there's an uncountably infinite number of real numbers, and rational numbers are also infinite, and what we represent is just a small finite subset of all the rational numbers. So one thing that's sort of unusual is that we have two representations of 0. So you might think of these two representations of 0 as being infinitesimally close to 0, either on the positive side or the negative side. But just be aware that we have two representations of 0. So what does it mean for equality? most importantly, the results may not be exactly representable. So the result of a particular operation is not mathematically correct, if you will. Close, but not exact. Another thing that is really confusing is that the associativity that you're so used to with math doesn't always hold. So with floating point numbers, this computation here is not always correct. Okay. The other thing is that we have overflow and underflow leading to both infinity and zero. But I do want to point out that one thing that's true is that every 32-bit integer, whether signed or unsigned, can be represented exactly with a 64-bit double precision floating point number. So there's a bit of light for you. So to conclude this video, I gave an introduction and overview of the IEEE 754 floating point standard. In particular, I talked about single and double precision floating point values. And I showed how they were represented with bits, either using 32 bits for single precision or 64 bits for double precision values. I talked about how normal values were represented, and I also talked about the special representations for positive and negative 0, as well as for positive and negative infinity. I described denormalized or subnormal numbers, which are very close to 0, and I also described various rounding techniques and talked about some exceptional conditions that can arise during computations. So that concludes this video. I want to end by saying thanks for watching, and I hope to see you in my next video.